uniform transcendentality and correlation functions in any course for super MLs. Please start.
Yeah, so thank you very much, Rio. And I would like to join the other organizers the other speakers in thanking the organizers for putting together this great meeting. Also for moving the social dinner from Wednesday to, to Tuesday, which was great news for me. And finally, to give me the opportunity to present my work here, even though it's not truly connected to integrability, although of course I hope that some of the results that I'm going to present to you will be useful or interesting for the integrability community. And of course, at least we are working in the same playground, namely n equals to 4 super MLs. So let's get started. This is the plan of the talk. I will start introducing two-point functions of certain protected operators in n equals to 4 super MLs, where I will argue that uniform transcendentality kicks in somehow. Then I will further present some other perturbative relations and the conjectures that I put forward in this context. And finally, I will put this in a broader perspective, namely explaining why I was computing certain things. And this is three-point functions in n equals 4 super MLs, which of course might be of some greater interest for integrability. So let's start with the two-point functions. In fact, this talk is probably going to be the simplest of the whole program. And I will compute arguably the simplest object ever, namely the simplest correlator of the simplest operator in the simplest quantum field theory. That is the two-point function of the 20 prime operator in n equals 4 super MLs. And of course, given the premises, the result is also simple, perhaps exceedingly simple. It's three-level exact, thanks to non-renormalization theorems, which also extend to three-point functions, which were sort of a big deal in the late 90s. They allowed for early tests of the ADS-CFT correspondence. But perhaps for this community, they're a bit boring. Integrability people like anomalous dimensions, like quantum corrections. So in order to get something a bit more interesting, I will spice it up. But in order to do that, I will do two things which you might not like. One is moving away from for dimensions, so we'll consider a sort of dimensionally regularized version of this correlator, even though there's no need for that. The correlator is perfectly finite. But however, doing this will introduce quantum corrections in this sort of norm of the 20 prime operator, which of course are epsilon dependent, and in the epsilon goes to 0 limit, they recover the non-renormalization theorems that I mentioned before. And the other thing which certainly you won't like is that I'm going to compute this norm by a very traditional Feynman diagrammatic computation. So you might wonder why I was considering this object, which is sort of a normalization of an operator, not so physical. The truth is I was using it as a sanity check for a larger computation that hopefully I'm going to present to you later. So just bear with me with a couple more slides, and then we will see that we can get some mileage out of this calculation. So to be precise, I will compute this two-point function in momentum space, just because it's computationally easier. And I will adopt a specific regularization scheme, which is dimensional reduction, which has been argued to preserve supersymmetry. And also I will sweep all the log pi Euler gamma numbers under the carpet in the definition of the integrals. So I had already computed a couple of terms of this two-point function a few years ago. And these terms, to me, displayed some sort of pattern, which was screaming at me, please compute me at higher order in epsilon and higher order in perturbation theory. And last year, finally, I found the courage to perform a three-loop computation, which I'm going to present to you right now. In order to make it clean, I separated the three-level contribution. And then there are these three terms which I computed, which I expressed in terms of the 't Hooft coupling, just because there are no non-planar corrections up to 3 loops, even though I have not been considering any planar limit. So this is the one-loop result expanded to some high power of epsilon. There's no real need for that because there's a closed form in terms of gamma functions. I just did that in order to display this fact that if you associate a degree of transcendentality in the usual manner to zeta values, and also -1, as is customarily done for the dimensional regularization parameter, then you might check that all these terms display uniform transcendentality. Okay, you might say this is just an artifact because it's one loop, it's too easy. So in order to check it further, I also computed the two-loop results where multiple zeta values start to appear. And again, you can see easily that it respects uniform transcendentality. In this case, there is no closed form in terms of gamma function. There is one in terms of a hypergeometric. It's a bit more complicated, but it's cleaner if you expand everything. And finally, I push the computation with some effort up to 3 loops. And again, you can check that this result displays uniform transcendentality degree 6. So for me, this was sufficient heuristic evidence to put forward this conjecture, namely that this object that I am computing, the 2-point function of 20 prime protected operators in n equals 4 superior Mills, possesses uniform transcendentality degree or weight 2L to all loop orders. Of course.
Do you get all kinds of zetas or only a single valued zeta?
No, there are also multiple zeta values, yes. Starting from 2 loops. Oh, sorry. This is not the point. Starting from 2 loops, multiple zeta values start to appear. Yes, and then, of course, at 3 loops, there are more.
There are things called, how's it called, single valued zeta values.
I haven't checked if you can rewrite it in that way, to be honest, yes. But yeah, thanks. So moving on, of course, I was worried that if one computes this object to some higher degree in perturbation theory, then of course some non-MZV values are meant to appear, at least in the integrals which contribute to this object. And then if the conjecture is true, one has to cook up some definition of uniform transcendentality for those. But it could also well be that they finally don't appear in the final result, that they will just cancel out. I just don't know because I haven't computed to sufficient precision. So another comment is that the previous expression can be simplified a bit, basically absorbing all the even zeta values in terms of the odd ones. So there is this very funny looking and probably horrific for a mathematician perturbative redefinition of odd zeta values, which was first observed by Baikov and Chetirkin to make the QCD beta function free of any even zeta values. And this, of course, also works for my result because it can be implemented at the level of the integrals. You have to switch to another regularization scheme, which is called the G scheme, which I don't like because it obscures a bit uniform transcendentality. But still, you can get a more compact expression, of course, because you are eliminating all even zeta values. So another comment is that, of course, one natural question is that is wondering whether we can resum or find a closed pattern for all the leading terms, which I had highlighted with a red circle in the previous slides. So I had 3 data points, and I asked the online encyclopedia of integer sequences if she could find an answer for that, and she can. I mean, there's a factor there, which I'm reproducing here in greater detail, which looks perfectly reasonable. I mean, this is something which could well appear out of a Feynman integral calculation, multiplying some odd valued zeta number. So this is my conjecture. Of course, this is limited to the planar limit. I don't know what happens away from it, and possibly there will be subleading corrections starting for loops. I have no control on them, of course, even with a conjecture, but I still hope that they will display uniform transcendentality, as, for instance, happens in the cusp anomalous dimension. So given this conjecture, you can also expand it to a higher order, and for instance, for loops, in principle, a perturbative computation would be possible. It would be prohibitively difficult. For sure, I'm not able to do that, but in principle, the relevant 5-loop integrals are available. They have been computed by Alessandro and collaborators. But another thing that you can do is to perhaps try and resum this conjecture just by using the integral definition of the zeta function and switching the order of the integral with the sum. And so you can get an alternative form in terms of this integral over a hypergeometric function. And both the first expression and perhaps the other one somehow to me looked reminiscent of supersymmetric localization. For instance, the first one is very similar to similar results for n equals to 2 correlators computed via localization. But of course, since I'm computing things in sort of dimensional regularization, one would need a notion, a prescription for implementing dimensional regularization in localization, which I thought was completely impossible, but of course I was wrong, and Joe had already done it, as he pointed out to me a few days ago. And I deeply apologize because I didn't recognize the existence of this paper, so I didn't even cite it in my article shamefully, and I deeply apologize for that. But actually, it turns out that Joe, Alessandro, Anton Nedelin, and Song Kao Wen managed to expand this proposal that they have for the dimensional regularized version of localization result. And actually, it matches perfectly with this leading order term. Yeah, I apologize, the laser is not working, but okay. I'm pointing out with the finger, hopefully. Of course, away from the leading term in epsilon, then the other subleading terms are not meant to match, since no conformal mapping can be done from the sphere where localization is done to the flat space calculation that I have been performing. But still, it's remarkable that this first conjecture, which I cooked up just with 3 data points, was actually proven by localization methods. So another extension would be, of course, to try and compute 3-point functions of 20 prime operators, which of course are again protected, but I could compute them in dimensional regularization. But such a computation is too difficult, so what I did instead was to consider a limit, a soft limit, where one of the momenta of the operators in Fourier space goes to 0, which dramatically simplifies the calculation. So I was able again to push it up to 3-loop order. And I was hoping that it would display again maximal transcendentality, but it doesn't. Although the factor by which uniform transcendentality fails is a very simple one. It's -1 plus some coefficient multiplying epsilon. And just by computing order by order, it's very easy to infer the sequence of what this... no, actually, it's very faint, almost invisible. So. Yes? Ah. So I'm not transparent to this frequency. Yeah, good to know. Thanks. So it's very easy to infer how this sequence will continue. And this is a remarkable property which appears already at the level of the Masteric integrals. So all these coefficients basically are multiplied by a factor, for instance, at 3 loops, which is just -1 plus 8 epsilon. And this prompted another conjecture, namely there is a sort of perturbative relation, a very strange one, given in terms of a term which depends on the loop order and the dimension, between the soft limit of the 3-point function and the 2-point function. This is an exact relation. It doesn't entail any expansion in epsilon. It was not self-evident to me, although I believe there might be a way to prove it. However, this epsilon-dependent part is a bit strange. I mean, I don't know if this proof could also include these epsilon subleading terms. Anyway, from the perturbative standpoint, this relation connects basically the same diagrams, the same Feynman integrals, but with different powers of their propagators. This is an artifact of implementing the soft limit. And these powers can also be reinterpreted as the action of some differential operator. So I was wondering whether perhaps these perturbative series obey some differential equation. I don't know, but perhaps it could be used to harness it and bootstrap some results. This is like in my to-do list, along with trying to prove these perturbative relations. And other things, other extensions, for instance, trying to extend this to other higher dimension protected operators in N=4 superior Mills, or perhaps extending these uniform transcendentality conjectures to other theories. And one natural candidate would be a BJM in 3 dimensions. So there, the 2-point function was already computed to the leading order. One should just sit down and expand it in epsilon, which I haven't done yet, but it's totally within reach. And one interesting thing that might occur is that if uniform transcendentality is there, one conjecture that is valid to all orders in epsilon, and this could be actually used to help evaluating this non-planar integral, which is usually the toughest one to evaluate. And usually this is done by the dimensional reduction relations of Roman Lee, numerically, and then one extracts back the coefficients analytically by the PSLQ algorithm or the LLL algorithm or stuff like that. But if one can find a way to remove all the lower transcendental parts, given this conjecture that the sum with some coefficients could be maximally transcendental, then of course it's much easier to infer the analytic form of these coefficients, because one can just cook up a basis of uniformly transcendental numbers to use these numerical algorithms. And I would like to conclude this first part of the talk dealing with uniform transcendentality, just pointing out somehow that there is perhaps a strong relationship between integrability and transcendentality. Transcendentality has always been there since the inception of integrability, as you might read here in the first chapter of the Gospel of Nicholas. And the observation, of course, was that the anomalous dimensions of twist 2 operators n equal for superior meals can be expressed in terms of harmonic sums of uniform weight. And of course, transcendentality also played a crucial role in one of the milestones of integrability, namely defining the dressing phase. So uniform transcendentality is really important. It's really ubiquitous somehow in n equals 4 superior meals. It also appears in scattering amplitudes and for factors, allowing for their amplitude booster program of Dickson and collaborators. It's there. It's pivotal for Feynman integral evaluation if you follow the canonical form method of Johannes Henn. And yet, its deep origin is still quite mysterious and not fully understood. So I leave this as a thought-provoking or a sort of, message for something which I think is really important to understand n equals 4 superior meals. Okay, now I will switch gears, and in the remaining 7 minutes I will present the general framework explaining why I was computing this stuff. And this was for dealing with 3-point functions. 3-point functions are notoriously difficult to evaluate, even perturbatively, in any quantum field theory, but of course, if you restrict to a conformal one, then you just have to compute the structure constant, and you can do it with the OP method, which is really, really powerful since there is knowledge of, for instance, 4-point functions of protected operators up to an astounding level in perturbation theory, and this allowed for amazing results up to 5 loops for the OP data. For instance, of the structure constants of 220 primes and one twist 2 operator. But of course, if you go away from this simple limit, then things start to become a bit more difficult. But fortunately, thanks to these very clever people, higher point functions of protective operators have become available, at least at the integral level, from which, in principle, you can extract more general structure constants with more non-protected operators. But of course, the extraction of these structure constants becomes a tough job, only done by really, truly OP professionals. But more in general, I was puzzled by the fact that almost no direct computation of 3-point functions was available with the traditional methods in n equal 4 superior meals or any other theory for what matters. So I was wondering whether I could improve a little bit on this. And in order to do that, I resorted to this trick, which was proposed by Jan and collaborators 12 years ago. And this is extremely simple. One just takes the equation establishing the conformal structure of the 3-point function and integrates over the position of the insertion of one of the operators. And what this integration does in Fourier space is that it's totally equivalent to a soft limit. That's why I was considering the soft limit in the examples that I showed before. And what this soft limit does is essentially to transform a 3-point function into a 2.1, just because there is no inflowing momentum in one of these legs. Of course, the legs gets a bit modified, and for instance, if you consider this propagator and this as a soft limit, you will just see basically a double propagator, a propagator with a double power instead. But the real advantage of considering 2-point functions is that they are incredibly more easier to evaluate in perturbation theory, thanks to a plethora of methods which have been developed in years of phenomenology research. And so you can really deploy this heavy artillery against 2-point functions. And this makes the method really powerful. There are some limitations to the scope to which this method can be applied. And especially, there is a regularization issue since these integrals are generically divergent, so you have to dimensionally regularize them. And this brings in some complications which limit a bit the scope of application. But when it's possible to apply it, and it's easy to see where, then the technique is rather powerful. And I will show you now the results that I got deploying these methods over the last few years. So I focused on this sort of three-point functions, which seemed like the next two simplest thing that I could compute, namely 120 prime and two spinning operators. And back then I thought that my method would be the only one to able to infer this structure constant, since there were no explicit results for 5-point functions of protected operators away from one loop. So again, starting from one loop, I derived a few results, and from them, just heuristically, empirically, I was able to cook up these ansatz for the generic form for generic spins up to a coefficient, which I wasn't able to fix, but of course here I was outperformed by Pedro, Carlos, Alexander, and collaborators who not only could fix this coefficient, thereby giving a complete result, but they were also able to find a better basis for, reformulating, reshuffling a bit the roles of this polarization structure constants in such a way that it exposes that they can be expressed in terms of uniform weight harmonic sums, which my expression doesn't make explicit. So I was very envious, of course. But then I said, okay, and one other thing that they did, which is very important, is that they were able to find a complete and generic expression for the large spin limit of these sort of three-point functions, and they computed it exactly for any values of the 't Hooft coupling. And somehow the one loop results is in agreement with this formula. So then I extended the computation also to two loops. It consists of a transcendental part proportional to z of 3, whose coefficient can be inferred pretty easily from some empirical data. And I was hoping that the rational part could also be expressed in closed form, and that's why I computed this object up to spin 12. However, I wasn't able to find some expression which could match these big rational numbers somehow. So this first coefficient, like the simplest one, where there are two Konishi descendants, was also confirmed by an integrability computation, again by Pedro, Carlos, Alexander, and collaborators. But of course, this very year, I was completely outperformed here. Carlos and collaborators computed these same objects via an OP approach. They had lots more of data. And with those, they also clarified how this strange dependence on the spins appearing here morphs into the generic form which they found for the large spin limit of these objects. So there is like a subtlety in taking the OP limit or the large spin limit, and they clarified how this works. And yet, even though they possess many more data than I did, apparently this rational part is still resisting a complete formulation in terms of some generic sums. So I was considering a simpler object in the hope of being able to find a closed expression. So I substituted one of the spinning operators with a Konishi scalar, just the one of dimension 2. And I was hoping that having only one spin, I could find a closed expression. But again, even though I reached spin 24, I wasn't able to find a pattern. Yes, so this is becoming my nemesis, but okay, never mind. By the way, I never published this because I thought that just the numbers were not so interesting, but perhaps if there is somebody who might use this data somehow, just let me know and I can give them to you. And so in the final slide, yes, I was also able last year to push the computation of this structure constant up to 3 loops. Of course, I limited the computation to the simplest one, which is spin 2 operators, the Konishi descendants. And these are the results for the 3 polarizations possible of the structure constants. So of course, I performed extensive checks, since in order to derive this result, there are order 10,000 diagrams that you have to sum. So of course, the probability of making mistakes is very high, and in fact, in the first version of the paper, I had made a mistake, shamefully. But it was not detectable with my checks, and the checks were, for instance, reproducing the anomalous dimension of the Konishi and its 3-point functions with 20 primes in perturbation theory up to 3 loops. And these are completely independent data because the ones to which I compared are derived by the OP. So this is also a new derivation of them using purely traditional methods. And of course, one of the checks was that the 3-point function, when this Konishi is substituted by a 20 prime, is in fact 1, and this I checked, prompting the computation that I showed you before and that display uniform transcendentality. And it's 25 minutes, so this is just the final slide with my conclusions, stating some outlook of things that I would like to compute and which are within reach of my method. I would like to extend the computation to higher twist operators, especially because they will naturally include one-over-n corrections, which are notoriously difficult to derive with other methods. And so I would really like, I hope that my method is powerful enough to disentangle mixing, clarify the role of multiple traces. And so, yes, that's something that I would like to pursue. And of course, another avenue of research is pushing the computation at 3 loops in such a way to include spins greater than 2. For doing that, I will have to optimize a bit my calculational method to have them in a finite amount of time. And since there is no OP limit yet available at 3 loops for 5-point functions, my method would be the only one for now able to compute them. Of course, I'm waiting for the usual suspects to outperform me again with their more powerful methods. But in general, the philosophy of this line of research was to provide experimental data that potentially could be useful for comparisons with integrability or prompting some new developments. And with this, I'm done. Thank you very much for your attention.
Thanks, Marco. Any questions?
The conjectures. So supersymmetric theorems, it's suspicious to make conjectures up to a certain loop order in supersymmetric theories because eventually the supersymmetry doesn't help you. So I can give numerous examples of that. Is there some where the D terms start to appear in the supersymmetric theory? Is there some loop order at which you might expect to see problems?
For the computation that they've been performing, I'm not sure that will be an obstruction. There are several examples, for instance, in scattering amplitudes where that is not a problem.
Can you give an example?
So, for instance, MHV and next to MHV amplitudes are supposed to be uniformly transcendental to Lorder, at least.
When you say supposed to be, what does that mean?
Say again?
You say they're supposed to be. Well, has it been proven?
There is a sort of proof by the Arcaniamet group using their Grassmannian formulation. So, you have to be careful of what's the meaning of proof. Of course, there will be some assumption, but if you believe their formulation, in principle, that predicts that all the amplitudes next, I think MHV and next to MHV, would be uniformly transcendental to all loop orders. Okay. And of course, away from that, it's not really known, but for instance, the amazing results of Dixon seem to corroborate that because they cook up a basis of uniformly transcendental functions, but then they're perfectly consistent with the unitarity cuts or all the things that they use to fix their coefficients. So,
and if you do n equals 2, for example, what happens instead of n equals 4?
N equals 2 seems to break uniform transcendentality, for instance. There is already evidence.
At a certain loop order or at all loop orders? Is there a certain loop order at which it breaks down?
No, I think it depends probably on the observable, but 2-point functions, for instance, of the same object, of protected operators, have been computed, and I think that they started displaying deviations from uniform transcendentality at very low orders, like 2 or 3. So, but yeah, I agree with you. It's a bold conjecture.
Okay.
Yes. What can I say?
Okay. Thanks.
But somehow Joe's computation seems to support it, at least for the leading epsilon term. Which, okay, I agree, it's not so much, but it's something.
How does it behave at strong coupling? The resummation.
I haven't really checked because I didn't have anything to compare with, so I didn't think it was so interesting to perform any and expansions or everything. So I cannot answer, but
But should it have a dual at strong coupling? Should it have a picture at strong coupling?
I mean, yeah, we don't know. I guess so, but doing it in dimensional regularization perhaps is a bit tricky. I mean, I don't know. There might be some prescription to do that, but
People did, right? I mean, Maldacena and Aldai, for example, they did it.
that's true. Yes, they have a prescription for implementing dimensional regularization in for scattering amplitudes. Yeah, that's right. I wouldn't know how to proceed, but I guess there must be some way of doing it. Yes.
So, thank you. Very nice results, nice talk. But I didn't quite understand the relation, the connection between the first part and the second part. So I mean, if you
Yes.
do epsilon regularization, yeah, you are not very explicit on it, yes. If you do epsilon regularization of protected correlators, you extract unprotected information, yes, some operators with derivatives, etc. That's the method, essentially. And then you, for example, the 3-point functions correspond to some higher powers in epsilon expansion. That's the idea?
So no, the idea, I mean, it was really stupid. It's just that, so my real objective was to compute 3-point functions, right? In order to do that, I had to compute stuff in dimensional regularization. And in order to perform checks of my computation, I also computed correlation functions 2 and 3 points of protected operators, because I wanted to check that they are not renormalized. But then doing that, I exposed this structure which looked interesting to me, because it displays some regularity, some pattern, uniform transcendentality, and so I pushed the computation to higher order. So that's just the connection. I mean, I stumbled on this result by chance doing something else. I was computing other stuff, and then I discovered that. That's just the connection. Apologies for not being...
What is precisely the relation between these higher powers of epsilon expansion of protected operators and unprotected?
No, I wouldn't say there is any relationship. I mean, it's just the same playground. I mean, I was computing this stuff in perturbation theory, so I had to use dimensional regularization in order to do that. And then this happened, but I don't see any specific relationship between 2 or 3-point functions of protected operators with those which are not protected. If that's your question, sorry, I'm not sure I...
Okay, maybe ask later.
Okay, sorry.
Maybe a little question more. Say we considered in our last paper with Pedro and Harish these big operators. Would it be possible to do something at least at one loop for huge operators actually?
So usually huge stuff, I know it's a blessing for integrability, but it's a bit of a nuisance for traditional methods. So, but perhaps at low loop order, yes, some perturbative computations are possible. I guess so, yes. But of course they will be much inferior compared to other methods or integrability. So I don't know if it's an interesting thing to check, but yeah, why not?
Okay, thank you.
Was going to add a comment on Pedro's question. I think it goes as a log of G. So if you want a strong coupling, there is a log of G, and you can rewrite this 3F2 as like a Tracy Widom. So it's always like a Bessel kernel. So there are 2 Bessel functions, and then the usual exponential kernel. So
yes, that's true. In fact, you told me yesterday. Apologies, I should have replied. I knew the answer because Alessandro told me yesterday, but yeah, I have forgotten, sorry.